was in the distant reaches of our solar system beyond the orbit of Neptune. The James Webb Space Telescope turned its gaze toward the Kuiper Belt, a vast region populated by icy bodies and remnants of the solar system's formation. Stationed at the second Lagrange point, nearly 1.5 million kilometers from Earth, the telescope was conducting a survey to study the composition and dynamics of these distant objects. Its near-infrared camera, designed to capture faint light from the cosmos, was scanning a sparse patch of the belt when it detected something unexpected, a faint, uncatalogued object moving against the backdrop of stars. The object was small, larger than a few kilometers across, but its behavior stood out. Unlike the typical Kuiper Belt objects, which follow predictable elliptical orbits, this one moved with a peculiar trajectory. It was faster than expected for an object at that distance. Its path slightly curved, suggesting influences beyond the sun's gravity alone. The telescope's instruments, recalibrated to track the object, revealed a surface that reflected sunlight differently from the icy, dusty bodies common in the region. Its albedo, the measure of reflectivity, was higher than that of typical Kuiper Belt objects, hinting at a composition that might include metals or crystalline ices. Astronomers at Mission Control, intrigued by the anomaly, directed the telescope to gather more data. The near-infrared spectrograph began analyzing the object's surface, detecting signatures of water ice mixed with compounds that were harder to identify. There were traces of silicates, possibly similar to those found in meteorites, but also faint signals of organic molecules, which are rare but not unheard of in the Kuiper Belt. What puzzled the team was the object's thermal profile. It emitted a slight infrared glow, suggesting an internal heat source or a surface that absorbed and re-radiated energy in an unusual way. This was not the behavior of a frozen, inert body. As the object continued its journey, it passed close to a known Kuiper Belt object, a dwarf planet candidate, roughly 300 kilometers in diameter. The interaction was subtle but measurable. The object's trajectory shifted slightly, as if influenced by the gravitational pull of the dwarf planet, but the change was not entirely consistent with a simple gravitational encounter. It seemed to adjust its path, slowing briefly before resuming its course. This behavior raised questions. Was it responding to unseen forces, perhaps a faint outgassing of volatile materials? Or could it be something more complex, like a loosely bound conglomerate of materials reacting to external stimuli? Ground-based observatories, including the Atacama Large Millimeter Array in Chile, were alerted to confirm the observation. Their resolution, however, could not match the precision of the space telescope's instruments. The data from Earth showed a faint blur, consistent with the object's small size and distance, but offered little clarity. The team relied on the telescope's detailed imagery, which revealed the object's shape as irregular but not chaotic, like a lopsided sphere rather than the tumbling fragments typical of collisional debris. Its surface appeared smooth in places, with patches that suggested erosion or alteration over time. Unlike the pristine ices of other Kuiper Belt objects, the object's motion continued to defy expectations. It followed a trajectory that took it slightly above the plane of the solar system, a path that required more energy than a typical orbit would suggest. This deviation was small but significant, prompting speculation about its origins. Could it be an interstellar interloper, like Oumuamua, which passed through our solar system in 2017? Unlike Oumuamua, which tumbled and showed no signs of activity, this object moved with a steadiness that suggested stability. Its velocity, while high, was not consistent with an object escaping the sun's gravity entirely, ruling out a purely interstellar origin. As the telescope tracked the object over several days, it detected faint variations in its infrared emissions. These were not random fluctuations but showed a pattern, a subtle rise and fall in intensity over a period of hours. The team hypothesized that the object might be rotating, exposing different surfaces to the telescope's view. The periodicity suggested a rotation of about 10 hours, slow for an object of its size but not impossible. The variations could indicate differences in composition across its surface, perhaps regions of ice interspersed with darker heat materials. The scientific community buzzed with cautious excitement. Teams from various disciplines began analyzing the data. Planetary scientists considered whether the object could be a rare type of Kuiper Belt body, perhaps one formed in a unique environment during the solar system's early days. Chemists puzzled over the spectroscopic signatures, which hinted at complex hydrocarbons not typically seen in such distant objects. Dynamicists modeled its trajectory, trying to reconcile its path with known gravitational influences. The object's behavior suggested it might have been perturbed in the past, perhaps by a close encounter with Neptune or another large body. One theory proposed that the object was a fragment from a collision in the Kuiper Belt. Its unusual properties, resulting from exposure to high-energy processes billions of years ago. Another suggested it could be a captured object, originally from the outer reaches of the solar system or even beyond, trapped in an eccentric orbit. The possibility of internal heat, though faint, led some to speculate about radioactive decay within its core, a process seen in larger bodies like Pluto but rare in smaller objects. no hypothesis fully explained all observations, leaving room for debate. The telescope, not designed for prolonged tracking of fast-moving objects, struggled to keep the object in view as it moved farther into the Kuiper belt. Its instruments captured one final dataset before the object's angular motion exceeded the telescope's tracking capabilities. The data showed a slight increase in reflectivity as the object turned, possibly exposing a fresher surface. There was no evidence of outgassing like the jets seen in comets, nor any debris trail, which ruled out a cometary nature. The object remained enigmatic, a puzzle that defied easy categorization. In the weeks that followed, researchers scoured archival data from other missions, including Voyager 2, New Horizons, and ground-based surveys, looking for similar anomalies. A few candidates emerged, faint detections of objects with unusual orbits or spectra, but none matched the precision of the telescope's observations. The event prompted a re-evaluation of how we monitor the Kuiper belt, a region less studied than the asteroid belt but critical to understanding the solar system's history. Current surveys, like those conducted by the Pan-STARRS telescope, are designed to detect larger objects or those on collision courses with Earth, potentially missing small, dynamic bodies like this one. The observation raised broader questions about our ability to detect atypical objects in the outer solar system. The Kuiper belt, spanning billions of kilometers, is sparsely populated and difficult to observe comprehensively. If objects like this one exist, they may have gone unnoticed due to their faintness or non-traditional reflectance properties. The telescope's sensitivity had revealed a gap in our understanding, suggesting that the outer solar system might hold more surprises than previously thought. Researchers proposed new observation campaigns to target similar objects. Proposals included redirecting ground-based telescopes to focus on the Kuiper belt and developing algorithms to sift through existing data for anomalies. Some suggested that future missions, like a dedicated Kuiper belt explorer, could provide more direct observations. The event underscored the need for advanced tracking systems, as current telescopes, including the James Webb, are optimized for deep space imaging rather than dynamic objects. The object's discovery, though fleeting, left a lasting impact. It challenged assumptions about the uniformity of Kuiper belt objects and sparked discussions about the diversity of materials and processes in the outer solar system. Astronomers began to consider whether similar objects could be remnants of early planetary formation, carrying clues about the conditions that shaped the planets. Chemists speculated that the organic signatures could point to prebiotic materials, offering insights into the origins of life. Even engineers took interest, analyzing the object's trajectory to refine models of orbital dynamics. The scientific community remained cautious, avoiding premature conclusions. The object did not fit neatly into known categories as comet or dwarf planets, but neither did it require extraordinary explanations. It was a reminder that the solar system, despite decades of study, still holds mysteries. The data collected during those few days of observation would be studied for years. Each spectrum and trajectory point scrutinized for clues. The object, now lost to the vastness of the Kuiper belt, had become a catalyst for new questions, driving scientists to look beyond the familiar. As the telescope resumed its primary mission, mapping distant galaxies and ancient stars, the memory of the object lingered. It was a fleeting glimpse of something different, a small but significant anomaly in the orderly chaos of the solar system. Whether it was a unique relic of the past or a hint of processes yet to be understood, it had captured the imagination of those who study the cosmos.